BAMOSS is an experimental test bed designed to study dynamic couplings between rigid modes and vibrating modes of a very light structure. BAMOSS is composed of a main hub, free in rotation around a vertical axis, and two flexible cantilever beams fitted with a point mass at each free end. Such a system figures a satellite with two flexible solar panels around its roll axis. We want to regulate the attitude, that is to say the angular position of the hub, and to servo loop this angular position to 0 degree. For this purpose, a torque can be applied to the hub using a torque motor. The actuator is located under the hub and is not visible. Three sensors are available: an optical encoder to measure the hub angular position theta, a tachymeter to measure the hub angular rate theta dot, a gyrometer located at one tip mass to measure its inertial angular rate around the vertical axis beta dot. The open-loop dynamic behavior of this system is characterized by three modes. The rigid mode represents the global motion of the whole system. The symmetrical flexible mode of the beams has a slow pulsation around 1 Hz. The desymmetrical flexible mode of the beams has a higher pulsation around 3 Hz. This mode moves the hub in rotation. The eigenmode notion is very important because whatever the external excitation on this system, its free motion will be a combination of these three modes. The symmetrical flexible mode cannot move the hub in rotation, so this mode will be unobservable from the angular position theta and rate measurements theta dot. This mode is also uncontrollable from the input u only, that is to say, the torque applied on the hub. Indeed, if all the modes are manually excited, it is very simple to drive to 0 the rigid mode, to perfectly damp the desymmetrical flexible mode, but there is no way to damp the symmetrical flexible mode. To evaluate the performance of the servo loop position, we are not going to study the tracking error to a position input reference, but rather study the perturbation rejection performance. Therefore, we are going to excite all the modes of the system. That can be easily done imposing initial conditions on the system. For instance, drifting the hub from its input reference position and setting an initial condition on the free end of one beam. Now we are going to record the three measurements and the control signal during 5 seconds in open loop and 5 seconds in closed loop. Exactly as in the manual test, we can see that all the modes have vanished in closed loop except for the symmetrical flexible mode. The recording of this test allows to display the hub angular rate theta dot, the hub angular position theta, the inertial angular rate at the beam tip beta dot, the control signal u. During the first 5 seconds in open loop, we can notice that only the desymmetrical flexible mode is visible from the hub angular rate and position. Symmetrical flexible mode is unobservable from these measurements. We can also notice a beat behavior on the beam tip angular rate beta dot. Such a behavior is due to the combination of the fast desymmetrical flexible mode and the slow symmetrical flexible mode. Once the control loop is closed at time is equivalent to 5 seconds, the hub angular rate and position are driven to 0. The beam tip angular rate measures only the residual and uncontrollable oscillation of the symmetrical mode. If we take care to excite the rigid mode and the desymmetrical mode only, we can see that the control low allows the rigid mode and the flexible mode to be driven to 0. Such a control low is a proportional derivative control low which feedbacks the hub angular position through a proportional gain Kp and the hub angular speed through a derivative gain Kv. This control law is called a collocated control law because it feedbacks the velocity, here the hub angular rate, at the structural location where the torque is applied, here the hub. If the beam tip angular rate is feedbacked instead of the hub angular rate, we obtain a non-collocated control law, which is always destabilized, as we can see from the following test. From an equilibrium state, we can see that the dissymmetrical mode becomes unstable when the servo loop is closed. Let us consider one more time the collocated control law. The following test aims at studying the step response. The step magnitude on the position input reference is 10 degrees. If the measurement sampling rate is fast enough, we can see that the tracking performance and stability are obtained. The recording of this test allows to check that the input reference is reached on the hub angular position. This test also highlights a non-minimum phase response on the tip angular rate, which can be physically explained by the beam deflection due to the initial torque. If the sampling rate is reduced from 50 to 5 Hz, we can notice that the collocated control law is no more stabilizing.